Okay, so yesterday we stopped here. So here we talk about the magnetic field line similar to the one in the similar to the one called the electric field line. So here you can see a similar graph. You can see a magnetic stick, and this is the north pole. This is south pole. So you can see the magnetic field line will somehow like this, and I think you should still remember the electric field line if you have a dipole. If you have a dipole, so a dipole is two charges, one positive and one negative with the same magnitude. So this is called the magnetic dipole. Magnetic dipole. So for a magnetic dipole, it should have some electric field line like this, like an apple. Somehow like this. So you can see this one and that one is look very similar. And actually, for magnetic, we cannot break it into a monopole. We cannot break it into a monopole. If you break a magnetic stick, it could become a small north and south pole, north and south pole. So it's still a magnetic dipole. And actually, till now, there are no scientific research can create a magnetic dipole. So which makes the Maxwell equation look a little bit different for the Gauss law for the electric field version and the magnetic field version. You can see for the Gauss law, if you still remember, you should remember because you need to take the midterm exam soon. So Q enclosed. So this is the Gauss law for the electric field. But for the magnetic field version, you learned it in chapter 32, so you don't face it yet. So for the magnetic version of the Gauss law, the right hand side should be 0. Actually, you can just divide by mu 0 or multiply on the ratio. But actually, that one is, this case, you cannot have a independent magnetic, so-called magnetic charge or magnetic monopole. You cannot, if you draw a Gaussian surface, you cannot have a magnetic charge, so-called charge or magnetic monopole. 实单极没有磁单极，电荷可以有正电荷、负电荷。So for a Gauss, surface, you can draw a Gauss surface like this, so that it encloses a positive charge, or you can draw a Gauss surface like this, and it encloses a negative charge. But you cannot draw a even if you draw a Gauss surface like this, then the total net magnetic monopole is 0. There should be nothing at the right side. So all the interpretation are similar to the electric field line, so we can just skip it. So here it mentioned the two poles, the closed field line enter one end and the magnetic field. So the north pole is just like the positive charge, and the south pole just like the negative charge. So as you can see here, in Wikipedia there is a tab called the magnetic monopole. So magnetism in bar magnets and electromagnetics is not caused by magnetic monopole. And indeed there is no experimental or observational evidence that magnetic monopole exists. 它并不存在，就是有些科学家就是假设它存在，然后写了另外一个版本的 Maxwell equation. So you can find it on Wikipedia actually, but actually magnetic monopole does not exist. Okay, here's an sample problem. So a uniform magnetic field B with magnitude 1.2 millitesla is directly vertical upward. So directly vertical upward through the volume of laboratory chamber. A proton with kinetic energy 5.3 MeV enters the chamber, moving horizontally from south to north. What magnetic deflecting force acting on the proton as it enters the chamber? The proton mass is neglect the Earth magnetic field. Neglect the magnetic field. So here we have a proton, which is a positive charge with one elementary charge. So as I mentioned before, here we use the mega eV as the unit of the energy, as the energy. So you know that if you have mega eV, you multiply it by, so it's just like so you have 1 eV, which means 1.6 times 10 to minus 19 joule. So if you have 5.3 mega eV, it should be equals to 5.3 times 10 to minus 10 to 6 times 1.6 times 10 to minus 19 joule. So this gives so somehow like 8 point something or 9 point something times 10 to minus 13. So for energy for a particle, for a charged particle, using the EV may be a better number rather than writing blah 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 times 10 to minus tens or something. So here, so first we just calculate the velocity of the proton, which should be 2k over m, and take the square root 2k. So because k is 1/2 mv square, right? So we have 2k, k is 5.3 times 10 to 6 times 1.6 times 10 to minus 19 over m is 1.67 times 10 to minus 27 quantity, take the square root. So the velocity is 3.2 times 10 to 7 meter per second, which is quite fast, which is around 1/10 of the speed of light. 1/10 of the speed of light. So you can't really ignore the relativity effect. But actually, we'll talk about the special relativity in chapter 37. After finish the electromagnetism. So we know the Coulomb's, not Coulomb force, Lorentz force. Lorentz force is Q V B, and then psi phi is actually 90 degree, VB VF, and then B is outside out of the page. So actually psi phi is 90 degree. Psi phi. So Q is 1.6 times 10 to minus 19, and then V is 3.2 times 10 to 7, and then B is 1.2 millitesla. and then sine 90 degrees, which is 1. So the answer would be 6.1. 6.1 times 10 to minus 15 Newton. So this is the force. So one point to talk about is that when you have the dot, which means the B field is pointing out of the page. If it is a cross, it is pointing into the page. So here we have V pointing upward and B is pointing out of the page. So the FB should be in this direction because it's a positive charge. So how large is the acceleration of the proton, which is very simple. You just need to use the Newton's second law of motion. So which is 6.1 times 10 to minus 15 over m is 1.67 times 10 to minus 27, which is 3.7 times 10 to 12 meter per second squared. So the acceleration is very fast. Okay, here we have a interesting stuff. Not sure right now.
The motion of a charged object in a constant electric field is very similar to the motion of a mass in a...
Okay, so, wow, stop. Okay, start play, no. Conceptual question. So let me try to config it a bit. So first of all, we can make we can make the velocity to be 0. No. Yes. Field charge mass, not this case. Positive charge. Clear trace. Where? Position X, Y, or B. Let me see. Oh, yeah, I see. Oh, there's a electric field here, so that's it look a little bit strange. It should be like this. I reset everything. 0. So it won't move. You can see here, the charge doesn't move. Because it still move. Oh. I'm not sure. Gravity, I don't think it should have gravity. I just need to create a trace. I suppose it should be good now. It should be good now. So I just let all the magnetic and electric field to be 0, so that it doesn't move anymore. It doesn't move anymore. So let me just increase the E to 4 V per volt per meter. So it will move down because this is a negative charge and the E is pointing to the positive side. Okay, so for the next case, if I just make this one to be 0, this one to be 0, and then the magnetic field to be 1, what will happen? What will happen? This one to be 1, this one to be 0. This one to be 0. What will happen?
Actually, what's the direction? I wonder.
What direction? What? Which is? Oh, okay. Direction. I'm not sure. Clear trace. Oh, this one is this one. Direction is pointing outward, out of the page. What will happen? Nothing happen, doesn't move because the charge doesn't move at all. So there are no Lorentz force. So let me do something else. I make the vertical velocity to be 8. So which means moving to the right side is the positive x-axis. So now how does the charge move?向上，咁樣。It should be somehow like this, because it has a vertical velocity. So actually, it's a circular move. Because actually, if at the starting point, V is pointing to that side, and then B is out of the page. So V cos B should pointing downward, and this is a negative charge, so the force pointing upward. So it will try to turning to the upper side. So as long as it turn to this point, which means the V point to upward. So V point to upward, so V cos B point to that side. So this is negative, so the force point to the left side. So you try to turn this way. So at the end, it will have a circular move. So how about if I decrease the speed? Decrease the velocity. Decrease or increase? Decrease. So if I just this is for 8. So the radius is double. So if I make this 0.4, what will be? Actually, I just show it to you. It will be interesting. Let's see. Well, 0.4. Get here. Maybe the speed is too slow. Speed is too slow, and maybe I can change the charge to be larger in magnitude. Let me see. What? Whoa. So you just like a helix, because if without the electric field line, without the electric field, it would have a circular move. So if now we have another electric field, we now have another electric field, so it will change the overall force acting on the charge. So it will not look like a helix. Or if I further change it, it will look like a very interesting. So okay, so let's come back here. Okay, so here we talk about the cross field. Just now I just showed you that if we have a magnetic field, uniform magnetic field, and then we have a initial velocity perpendicular to the field, so that the charge will actually have a circular movement. So the modern version of J.J. Thompson apparatus measuring the ratio of mass to charge for electron. So this is the way how it try to measure the ratio of mass to charge, m over e. So it generate a E field, which is like this. The E field and then the B field pointing into the page. So we have E field pointing downward. So we have a parallel plate, which is a capacitor. So it will have E field pointing downward, and then it also somehow generate a uniform B field. Maybe use a magnetic to generate the B field pointing into the page, so that the B field and the E field are perpendicular to each other. And also, it tried to emit an electron from here. Use some high voltage or somehow. So it tried to split an electron to the right side. And there is a slit here, so that try to control all the electrons are horizontally splitting out. If it is not horizontally, it will be blocked by this slit. So it will go in this direction. So in the plane. So if a charged particle moving through a region containing both electric field and a magnetic field, it can be affected by both electric force and magnetic force. When two fields are perpendicular to each other, they are said to be cross field. If forces are in opposite direction, one particular speed will result in no diffraction of the particle. So we can try to manipulate the ratio between the B field and E field so that there will be no force acting on the electron, and then the electron will go straight to this point. If there is some balance, there may be some force acting on it, then it will bend to one side, because you can simply imagine so considering the E field pointing this side, so that is a negative charge and electron. So the Coulomb force will pointing upward. So for the Lorentz force V is pointing to the right side, and then the B field pointing into the page. So so V cos B should pointing upward, and then Q is negative. So the Lorentz force pointing to the lower side. So the the Coulomb force pointing to the upward, pointing to the upward, and the Lorentz force pointing to the lower side. So if both of the force have the same magnitude, then they will cancel each other. If it is not, then the electron maybe go either upward or downward, maybe somehow like this or like that, depending on which force is larger. So of course the point for a balancing force is that QE equals QBB. So Q can be cancelled, so E over B should be equal to the velocity. Okay, so next we talk about the Hall effect. Hall effect is a very important experiment. So as we discussed, a beam of electron in a vacuum tube, vacuum can be deflected by a magnetic field. Can the drifting conduction electron in a copper wire also deflecting by a magnetic field? So here we can see this is a copper wire. So in 1879, Hall, then a 24-year-old graduate student, 是硕士生 at Johns Hopkins University, showed that they can, maybe I missed something. This Hall effect can allow us to find whether the charge carrier in conductor are positive or negatively charged. Beyond that, we can measure the number of such carrier per unit volume of the conductor. So actually, this experiment tells us that the moving charge in the conductor should be electron rather than the positive charge. This experiment really show that. So first of all, we assume the width of the copper is D and carrying a current I to the lower side. So whose conventional direction is from the top. So maybe we can imagine there may be a positive charge going from top to bottom rather than the electron going from bottom to top. Yeah. So the charge carrier are electron, and as we know, they drift in the opposite direction from the bottom to top. So as time goes on, electron move to the right, mostly piling up on the right edge of the strip, leaving uncompensated positive charge in fixed position at the left edge, as shown in Figure B. So the point here is that if there are no magnetic field, we can just apply some voltage difference or potential difference at here and here. So maybe this is a higher electric potential, lower electric potential, and there be current. Then all the thing will be fine because there will be no charge at either side because all the charge will try to go downward. So that's fine. But now if we apply a B field pointing into the page, then we find that still there are some current going downward. But now we can see that there are some negative charge at the right side and there are some positive charge at the left side. So this is really strange, and then we should try to explain this phenomenon. So so here we can imagine if there is negative charge, there's negative charge going upward, then we can imagine V cos B pointing upward and then B pointing into the page. So V cos P pointing to the left side, and this is a negative charge. So FB point to the right side, like this, okay? So we can imagine the negative charge will try to move to the right side, and the negative charge will start to accumulate on the right side. But this conductor should be electrically neutral because the current will try to go moving down. So if this is some negative charge on the right side, which means there is the same amount of positive charge on the left side. And in this case, this induced charge will generate an E field into this conductor, into this copper strip. So there will be an E field pointing from the left to right, somehow like this. It generates an E field like this. So in this case, as this is a negative charge, there will be some Coulomb's force acting on this negative charge. E pointing to the right side, this is a negative charge, so Fe should point to the left side. So as the negative charge start to accumulate, the E field will become larger and larger until Fe is as large as Fb, and then there will be no more charge accumulate at the right side because there are no net force acting on this charge anymore. Okay, get the point here? So it's until Fe equals Fb, and then there will be some voltage. This is Vd, not the voltage. This is the drift velocity. So as we can see here, V equals Ed. We can actually, so maybe I just go to when the magnetic field is applied to the conductor strip I with the field perpendicular to the direction of the current, Hall effect potential difference V set up across the strip. So because there is some positive charge on the left side, negative charge on the right side, there will be a potential difference on these two edges. So in this case, we call this voltage difference from the left side to right side V, and equals to E times D. So this is a formula in chapter 24. So V should be QE no. So for the point, if Fe equals Fb, Fe should be QE. Fe should be QE, and then Fb should be QVdB. So this is the Lorentz force. This is the Coulomb force. When they are equivalent to when they are equal to each other, then it is an equilibrium state， 就是达到平衡状态，就是当那个右手边的负电荷累积到一定程度之后，那 F1 跟 F2 就会相等，它们就电荷就不会再往右边跑，那左右的那个净力为0，所以它只会往上跑，就不会再累积，所以这个是平衡的状态的条件。Okay, so in chapter 26, we know that VD equals J over NE, and J equals I over A, which is the surface area, cross-section area. So here, cross-section area means this cross-section, because I is this direction. So A should be this cross-section area. So after we eliminate E and VD. So we try to substitute VD equals I over N here, and then we substitute E equals V over D here, and then Q and Q can be cancelled. So we have V over D equals IB over NEA. And actually, L equals A over D. L equals A over D. So A over D. Actually, we can substitute D. Maybe A equals DL. A equals DL. So we exchange DL, and D can be cancelled. So finally, N equals BI over VEL, BLE, BI. So we can get it like this. We make use of this one, and this one, so that we can get equation 28.12. So with this equation, we can find N from measurable quantities. When the conductor moves through the uniform magnitude field B at the speed V. So the Hall effect potential. This is called a Hall effect potential, which means that if we have a copper wire, if we have some current going through it, and then we apply a uniform B field perpendicular to it, then there will be some, if we apply a perpendicular B field, so there will be some potential difference at two sides. So this is called the Hall effect potential. So one point is that if the moving charge is positive, what will it be? If the moving charge is positive, which means the VD should pointing to the downside. So V cos B should point to the right side, which means that FB also point to the right side, right? So in this case, rather than negative charge on the right side, there will be positive charge on the right side. But it is contradict with the observation. This is contradict to the observation, and that's why the moving charge should be negative charge rather than positive charge. Okay. So let's see a sample problem. This is quite fast. Yeah. So a solid metal cube of edge length D equals 1.5 centimeter, moving in the positive y direction at the constant velocity of magnitude, 4 meters per second. The cube moves through a uniform magnetic field of magnitude 0.05 Tesla in the positive z direction. So this is V, this is B, this is B. So which Chap phase is at lower electric potential? And which is at higher electric potential? So they should be opposite side, but we need to really define. We do to find out that. So so actually, because V is moving to the upward, and constant. So and the B field onto this side. So even though there is no current going in it, but you can imagine if you have a cube moving like this, then there are some free electron. Which can be easily pushed by the Lorentz force. So which means that you can imagine there are some E, which is negative charge. So V onto that side, and E onto this side. So V cross B onto this side. V cross T onto the right side, and then Q is negative, which means that FB should point to the left side. So in this case, so this one will be negative, and then this one should be positive. So the left face should be negative charge, and then the right side face should be a positive charge. So now what is the potential difference between the phase of the higher and lower electric field? So it will be very easy. We just need to use this 28.13, V equals VBD. So VBD. So V is 4 meters per second, and then B is 0.05, and then D is 0.015. So V is 3 millivolt. So this voltage is quite small, but actually it is measurable. So that's